Hello and welcome back to Probability Theory. And as always, the first thing I want to do is to thank all the nice people that support this channel on Steady or PayPal. Today in part 9 we will talk about the important concept of independence. More precisely, this video is about the independence for events. For this, please recall we can visualize events as subsets in a sample space omega. So here you see an event A and an event B. Now in some sense, independence should mean that the two events don't affect each other. Whatever this means, in this example it's not clear at all because we have an intersection. Therefore, let's first look at a simpler example. So here we have two sets that are clearly disjoint. Hence, they don't have to do anything with each other, so we call them mutually exclusive. However, the question is, would we also call them independent? In general, we won't do that, and in order to see this, we have to think of probabilities. Namely, when we calculate the probability that A occurs, under the condition that B occurs, then this should be the probability of A itself. In other words, the event B should not affect the probability of A. So please remember, independence should mean that the knowledge of B does not make A less or more likely. And of course, this should also hold the other way around. So the conditional probability of B under A should be the same as the probability of B. Now, looking at the examples, we see it's not fulfilled for the second example and not clear at all for the first example. For this, please recall, the conditional probability here means what is the ratio of A inside B. And then the property tells us it should be the same as the ratio of A inside omega. And then of course, we also have to check this equality for B. Therefore, I would say let's visualize this in an example where we have some numbers to work with. So as before, we have a sample space omega and two events. And maybe let's choose 1/2 of omega to be the set A. Of course, please recall, this is only the visualization for the probability of A being 1/2. This means that we measure the sizes of the sets in the picture with the probability measure P. And now our idea is that we also split omega in half with the set B. Hence, the probability of B should also be 1/2. However, now the important question is, what can we say about the conditional probabilities? So first, what is the ratio of A in B? And of course, in the picture, you immediately see it's also 1/2. And on the other hand, we ask, what is the ratio of B in A? And in this case we see it's the same number, it's 1/2. Hence indeed we have the equalities here, so the events are independent. Okay, I think we have seen enough visualizations and we can start formulating the definition. And for this it's helpful to recall the definition of the conditional probability. So PA under B was given as P of the intersection divided by P of B. And similarly, P of B under A is given by the intersection divided by P of A. Now, for the independence, we want two things. First, this conditional probability should be equal to P of A, and this one should be equal to P of B. And there you should see, if we multiply this denominator to the other side, we have the same equality. Namely, the intersection is given by the product. And this is now what we can choose as the defining property for independence. So it's short and easy to remember. Okay, then let's put this into a definition. So the framework is the same as always. We have a probability space, which means a sample space omega, a sigma algebra A, and a probability measure P. And now we've learned we call two events AB from the sigma algebra independent if this equality holds. Then with this it turns out we don't have to restrict ourselves to two events. We can just consider a whole family of events AI. And indeed, we could have infinitely many when this index set I is infinite. And then also here, the whole family is called independent if it sends the intersection to a product. More concretely, we have P of this big intersection is equal to the product of the single probabilities. And this should hold no matter which finite subset of the index set I we choose. In other words, in this formula here, only finitely many sets Aj go in. However, you also see we need to check all possibilities here. Maybe the only thing you can ignore would be the empty set. Okay, then let's look what this means for a real-world example. So let's take an ordinary die and let's throw it 2 times. And then we look at the outcome with order. So we have a first throw and a second throw. Hence, our whole probability space has to represent this. So for the sample space omega, we have the Cartesian product of the set 1 to 6 with itself. Then in the next step, for the sigma algebra, as always in the discrete case, we just have the power set of omega. And finally, for the probability measure p, we have something we call the uniform distribution. This is not complicated at all, it just tells us that every element in omega gets the same probability. Or to put it in other words, the probability mass function is constant. So in our case we have 36 elements in omega, so we need 1 over 36. Okay, so this is the probability space, and now we can look at some events. In the first step I would suggest let's describe the events with words. A should be the event that the first throw shows a 6, and the second throw can show anything. On the other hand, B should be the event where we look at both throws and the sum of the numbers is 7. Okay, then in the next step, let's translate these descriptions into sets. For the first one, we just have a sample omega 1, omega 2, where omega 1 is equal to 6. Then for the set B, we also have the set of all samples omega 1, omega 2, where omega 1 plus omega 2 should be 7. Okay, since the sets are defined, we can calculate the probabilities. Of course, without much thinking, we immediately get the probability for A as 1 over 6. But you can also calculate it when you see we have 6 elements in this set, so we have 6 divided by 36. The same thing we can do for B, because we can list all the elements. So we could start with the element where the first throw is 1 and the second 6. Then in the same way, if the first throw is 2, the second has to be 5. And in this order we get all the possibilities. And we count 6, so we also have 6 divided by 36. So both events have the same probability, but this does not mean that they are independent. However, now using the definition, we can just check if they are independent. So let's simply calculate the probability of the intersection. So from all the elements in B, we have to take the ones that have a 6 at the first throw. And you see, we only find 1. Hence, the probability is 1 over 36, which is in fact the same as the product PA times PB. Therefore, our two events A and B are independent. Okay, maybe it's a good idea to look also at a continuous example. So here we take the unit interval and throw a point into it. Indeed, this is a typical and simple absolutely continuous example. And I think you already know how to choose the probability space. Of course, the sample space omega should be the unit interval. And the sigma algebra is the Borel sigma algebra. Finally, the probability measure we also call the uniform distribution. However, now we have it in the continuous case, which means instead of a probability mass function, we have a probability density function. Hence, this uniform now means we have a constant density function. And here, because we have the unit interval, we have the constant 1. As a reminder, this means when we want to measure the probability of an interval a, b, we have the integral over this interval of the density function, which should be b minus a. However, of course, this only makes sense if we choose b greater than a and ab in omega. I say this because often you see that the whole real number line is taken as the sample space. And then of course, in order to have the same thing, we have to change the density function. Indeed, this is what we then call the indicator function of the unit interval. It's written as such a one, where a set is in the index. The definition is very simple, we only have two values, either 1 or 0. And the important thing is, for all elements in this set here, so the unit interval, we are at 1. And otherwise we get out 0. Now in the case that the function is defined on the whole real number line, the graph looks like this. So we have one jump at 0 and one at 1. So you see, taking this as a density function, the sample space R would also work. However, this is just a side note, let's get back to our problem of independence. So let's take two independent events A and B. Then we know by definition that the probabilities fulfill this equality. Now let's use our probability measure and write the integral. So we have the intersection AB as the region we integrate over and the indicator function inside. Here, a nice property of the integral we can use is that we can exchange the sets. So we have the indicator function of the set a intersected b now, and 0, 1 is the region we integrate over. If you know the definition of the integral, you immediately see that this is correct. For probability theory, this is something we can use a lot. For example, we can also use it here on the right hand side. So first, let's fill in the definition of the probabilities here. And then, as before, we can simply exchange the roles. So what we get here is an equality of integrals. This integral here on the left hand side with the intersection goes to a product of two integrals. However, please recall, we really need the independence to have this. So with this you see, independence can be very useful in calculations. And of course, we will use that in later videos. Therefore, I really hope I see you in the next video about probability theory. Have a nice day and bye!